And the only thing that's changing in here, r is a magnitude, okay? And it's not going to change with time. It's the radius of our wheel. I is the unit vector in the positive x direction. That's not going to change with respect to time, okay? And omega is our angular velocity. If we take the derivative of angular velocity with respect to time, we get our angular acceleration. That's by definition, okay? So this turns into r times alpha I. And so we've got acceleration going in this direction of point C. Okay, so this is the linear acceleration of point C, and the minus sign just comes from the direction we've drawn the arrows. Okay, but it's r times alpha, and velocity of the center was r times omega. The acceleration of the center is r times alpha. Now that we've got the acceleration of one of our points, or a point on our rigid body, now we can go around and look at other places as well. Okay. So let's look at this one here. That's right straight down.
Nick.
And let's call this point B.
Nick, can you move to bottom water?
So if we look at the
Yeah,
acceleration
because
of
I'm
point B,
recording the lecture for Josh.
okay, we've got this equation here is equal to the acceleration of another point, which we know is point C, okay, plus the acceleration of point B relative to point C. We already just figured out the acceleration of point C. So this is minus r times alpha in the I direction. And this one here, we're going to replace all of this stuff here. Okay. So we've got alpha cross r minus omega squared times r. We could make a determinant out of this because it is a cross product, okay? Well, we could also say we know alpha is in this direction, and the r we're going in this direction. Now the r we're talking about is from point C to point B, so it's in this direction. Okay, so if we do this with our right hand, okay, we're taking alpha, which is this way, crossing it with r, which is this way. Our thumb's going in the positive I direction. Okay. You can also just say that this is k cross a negative j, right? And so k cross j, it would be negative I. We've got another negative, so we get a positive I. Or you could set it up as permanent. Okay. So either way we do that, okay, we're going to get from this one we're going to get alpha times r. Well, our distance is what I'm calling capital R. So that's just going to be r times alpha times I. Minus omega squared times r. This should be a vector. Okay. This r is going from C to B, and so that's in the negative j direction. So what we've got here for point B, these two are exactly the same but opposite in sign. So we get 0 there, and here negative negative gives us positive omega squared times r in the j direction. That should make sense. This is the tangential acceleration, okay? And we get some acceleration from point C, and then we get the opposite acceleration in this direction at point B. This is the tangential acceleration, okay? And it's going to be exactly the same as the acceleration at point C, but in the opposite direction, okay? So those two cancel out. This is the normal acceleration, okay? And it's always back towards the center of the circle, positive J. When we did velocity down at this point, the velocity at this point is 0. But the acceleration is not 0. So again, acceleration at point C, tangential acceleration, normal acceleration. At this particular point, the tangential acceleration exactly cancels out the acceleration at point C, okay? But we're still left with the normal acceleration.
Why was it a negative J in the
Because our R, this term here, this R vector, is from point C down to D, in the negative J direction. Well, let's look at another point. Let's see what I got on my notes. We can look at any point that works, or any point will work. It's just that we pick an angle other than 90 degrees, then it gets to be a little difficult, but other than that, it doesn't really matter. Okay, so let's go over here. Look, that's supposed to be a straight horizontal line. Call this point D. Well, we should be able to draw a picture, okay, a little bit, and then do the math to prove it. Okay, our acceleration of point C is still going to be this, okay, and so that means at point C we've got an acceleration in the negative I direction. Okay. Our acceleration at point D, this part here, this will be the tangential acceleration. So it's got to be in this direction, okay? And then this is going to be the normal acceleration. That's going to be back towards the center, okay? So these two, okay, depending on their magnitude, they're going to be in opposite directions. So they may cancel each other out totally, okay? But they will not add together. They will subtract from each other. And this one here will be in the negative J direction. At least that's the way it looks. All right. So let's do the same thing. AC plus AB with respect to C. Okay. And again, AC is what we know. Minus R times alpha in the I direction. Okay. And now we'll replace it with alpha cross R. Okay, alpha still is coming out of the board. R now is going in this direction. We're going from point C to point D. So R is in this direction. So if we're coming out of the board and we curl our fingers in the direction of R, our thumb's pointing down. That's our tangential. So it's going to be in the negative J direction. Okay? Or we can, alpha is K, and R is a negative I in this case. So R is a negative I. K cross I would be J, but we've got a negative, because R is a negative I. That's going to give us a negative J. So again, that's going to give us R